Hi, thanks for joining me today. In this presentation, I will be discussing our paper on high-dimensional geometric motion planning via gate-based coordinate optimization and local metrics. First, what is geometric motion planning? It is an approach that reduces complex locomotion problems, such as eel swimming or snake crawling, into geometric abstractions with finite shape modes or discretized segments for interpretable analysis, control, and motion planning using differential geometry and physical techniques. Take this simple three-bar linkage as an example. We can find optimal gates that maximizes efficiency for a given power consumption metric. The same principle can be extended from low-dimensional simple abstractions to high-dimensional models with higher fidelity that are more accurate and better represent actual robots. Examples include adding more links to better reconstruct snake-like curves and considering the whole body motion of the bipedal robot Cassie instead of assuming a single rigid body. However, the computational capacity of traditional method increases exponentially with the dimensions, making it almost infeasible. In this paper, we adjust the curse of dimensionality, thereby enabling geometric motion planning for high-dimensional systems. In this paper, we first recognize that the same geometric principles can unify various forms of locomotion environments, including momentum conservation in freefall, low or high Reynolds number swimming, differential drive mobile robots, and more. This is done by representing different nonholonomic constraints as local metrics and considering that when controlling the system's active components, the passive components flow along the minimum energy curve defined by the local metrics. Given a geometric model, we can perform gate optimization. This is a variational optimization that finds the equilibrium between maximizing the capture flux encoding displacements and minimizing the metric parameter encoding power consumption. Because this algorithm uses averaging theory, it requires a minimum oscillation coordinate called optimal coordinates. This coordinate can be considered a generalized center of mass. It optimally represents the motion of the system relative to the world and decouples internal joint motions. In previous work, optimal coordinates were determined by coordinate optimization, which solves partial differential equations over the entire shape space. However, this coverage leads to exponential complexity, making it almost infeasible for high-dimensional systems. This paper proposes the gate-based coordinate optimization, which combines coordinate optimization with gate optimization and solves the coordinate optimization iteratively by sampling along the current gate. This approach reduces the complexity to linear, making it scalable to high-dimensional systems. We apply geometric motion planning to two high-dimensional systems for testing. The first is a low Reynolds number swimmer with up to 12 links, serving as an abstraction for many aquatic animals. Its dynamics are dominated by viscous drag. The second example is Cassie, bipedal robot with up to 10 degrees of freedom, assumed to be in freefall or floating state, which can occur during the flight phase of running or jumping. Its dynamics are governed by momentum conservation. We want to find their optimal coordinates and gates for forward swimming and pitch reorientation, respectively. For low Reynolds number swimmer, compared to the coordinates attached to the central joint, the optimal coordinates better minimize the oscillations, reveal the true motion of the system relative to the world, and decouple internal joint motions, making geometric motion planning applicable and efficient. As shown in the figure, the optimal coordinates minimize oscillations in other directions and provide a consistent velocity estimate of the system. We perform gate optimization on models with different degrees of articulation. Clearly, at the same power level, a model with more articulation is more efficient, and its motion more accurately reconstructs the supinoid curves observed in nature. This suggests that models with more articulation have higher fidelity and highlights the importance of considering high-dimensional systems in geometric motion planning. Finally, we also studied the geometric interpretation of gate optimality in high-dimensional systems as a generalization of the optimal gate equilibrium in 2D. We first apply principal component analysis to the high-dimensional optimal gate for visualization. Now we can see again the equilibrium between displacement and power consumption on the left. Furthermore, on the right, we show that the gate subspace is aligned with the optimal subspace. Together, these two geometric interpretations demonstrate optimality of the gate. For Cassie's reorientation, compared to the coordinates attached to the torso, the optimal coordinates better reduce the oscillations, reveal the true motion relative to the world, and decouple internal joint motions again, making geometric motion planning applicable and efficient. The figure shows the exponential coordinates of the system rotation where the optimal coordinates minimize the oscillation in roll and yaw and highlight pitch rotation. We perform gait optimization on a partially actuated model that fixes some joints of the legs and the space between the two legs, as well as the fully actuated model that drives all 10 degrees of freedom of the robot. We can observe that the system with more articulation can perform more efficient gait at the same power level, and is closer to real human locomotion. This further emphasizes the importance of applying geometric motion planning to high-dimensional models. Finally, we also present a geometric interpretation of gait optimality for Cassie. Similar to the swimmer, the optimal gait finds a good equilibrium between displacement and power consumption as shown on the left. Moreover, the gait subspace aligns well with the optimal subspace as shown on the right, although the gait cannot expand further due to the joint limits. In conclusion, this paper takes a step towards geometric motion planning for high-dimensional systems by proposing a gait-based coordinate optimization method that overcomes the curse of dimensionality, and a unified geometric representation of locomotion that summarizes the modeling of different locomoting systems. We also present the implementation of geometric motion planning and optimality interpretation on two different high-dimensional systems. Future work includes considering continuum body modeling, taking non-zero net momentum into account, and generalizing the coordinate optimization for locomoting systems with holonomic constraints, like a walking Cassie. Thank you.